Hello everyone. In this video we will discuss numerical integration. So numerical integration is useful for definite integrals, so definite because we're using numerical here, we should get numbers out, that we cannot solve exactly. So some integrals, no matter what technique you have, U sub, integration by parts, whatever, you're not going to be able to solve this and write it in terms of, say, elementary functions like trig, exponentials, etc. So this is an example. So if you saw something like this, you would have no hope to solve this except to approximate it by using, say, Riemann sums. So we're actually going to go back to the basics and recall Riemann sums and how we define our integrals that way. So for different types of Riemann sums, we really have like four main ones that we think about: left sums, right sums, midpoint sums, and trapezoid sums. So I'll denote these by Ln, Rn, Mn, and Tn, where n is the number of subintervals that you have split your interval into. Right, so here's the picture. If we care about, say, the integral from a to b of f of x dx, then we look here, we have a, we have our b, and we split it into a bunch of subintervals, and we usually space them evenly. And so a would be your, say, x0, this is x1, x2, and so on until you get down to b, which is xn, and this point here is xn minus 1. And then to actually get the sums, we want to calculate the heights of these rectangles and then multiply them by the widths, right? So what is our width, first of all? Well, if they're evenly spaced, then our width, which we usually call delta x, is the length of the interval, b minus a, divided by number of subintervals, n. And so if we want a left sum, we start here at a, and we go all the way down until here. This is our last left endpoint. And so Ln is going to be f of x0 all the way down. We add up down to f of xn minus 1 all times delta x. Similarly, for the right ones, we start at x1, we end at xn. And for midpoint and trapezoid, there's similar expressions, but we won't need those for this introduction. So what we are going to do is put these in summation notation or sigma notation. So here's Ln. So how can we write this more compactly? Well, we're starting at 0. We're going up to n minus 1. And then what are we plugging into f? We're plugging in xi. And then we multiply all the terms by delta x. Similarly, we have f of xi delta x inside the sum for Rn. It's just that we've changed the indices. We're going from 1 to n instead of 0 to n minus 1. So the last thing that we should talk about here is how do you figure out the xi to plug in? Well, how do you find xi? So again, you have a, you have b, this is x0. How do you get to the next one? You add the width, delta x, right? And that's how you do it every single time. So xi starts at a, right? And then you're going I down the line, so you have I steps of adding delta x, or b minus a over n. And so this formula will tell you what you're plugging into f at each step. So now we're going to slowly work through this example. So cosine of x squared is one of those that we cannot evaluate exactly, so we're going to do our best to estimate it here. And we're going to do it, since we're going to use the power of Mathematica here, we're going to find L200 and R200, which are pretty big sums. So in this case, I have n equals 200, and b minus a is 1, so my delta x is 1/200th. And since I'm starting at 0, this is 0 plus I over 200, or I over 200 for my xi. So this means that L200 here, using my summation notation, is the sum from I equals 0 to 199 of cosine of xi, which in this case again is I over 200 but squared, right, because it's cosine of x squared, times delta x, so times 1 over 200. So to use Mathematica, this is what you would want to do for this sum. So it takes in your function here, and of course you need to actually plug in the xi, and then this will give you your lower bound, and this will give you your upper bound, and you just need to tell it the variable first. Okay, and so for this one, what you end up with is approximately 0.90567. So in the same way, we can compute our 200. So here the only thing you would change in Mathematica, right, is you would want to make that I1 200 instead of 0 to 199. And here we get approximately 0.903371. So from seeing those two numbers, 0.903-ish, 0.905 or 6-ish, we would guess it's something around there. The question is, do we know it lies between them? Is it just close to them? So we have a way of bounding our guess. So it turns out that cosine of x squared looks something like this between 0 and 1. Namely, it's always a decreasing function. And we should remember that if you have a left sum, right, all of these left endpoints are going to be higher than the right ones because you decrease from left to right. So this means that ln should be an overestimate for our actual integral, and rn should be an underestimate. So this means that we have our 0.903371 as an underestimate or a lower bound, and then here's our integral, and then it's between that and our 0.90567 from the left sum. Now you could make n larger if you wanted to get less error, and we'll talk about that next time in terms of getting as close as you want, but this is a good start. All right, so in our exercises here, we're going to work through this definite integral. So as I mentioned at the start, this is another example of something that can't be evaluated exactly, so let's try our best. So the first thing I want you to do is to write in sigma notation the sums L100 and R100. And here, remember, be careful, this is a 2, not a 1 this time, so it's at least a little bit different in terms of finding your delta x. Next, I want you to graph the function, because if we want to get an upper or lower bound, it would be nice to know if this is just always increasing or always decreasing on the interval, just like cosine of x squared was always decreasing from 0 to 1. And then lastly, I want you to use Mathematica to calculate L100 and R100. And as a helpful tip, do remember that e to the x, you can't just do like lowercase e to the x. You want to write that as, or let's just do negative x squared. It would be exp of negative x, and you could do your caret for the 2 to make it x squared. Alrighty, thank you for watching.